So today we will work our way through the deaths of stars. Actually, I like to think of it as there's two different stories to tell, right? Just like with everything else, either stars are dying or they're cooling off. Sometimes they do both. What are those two stories that we've been discussing this whole course long? Let's make sure everybody in here understands that. Back of the room. What's the central crisis, the heart of astronomy, the heart of astrophysics and cosmology that we've spent this entire course delineating? Come on, guys. Yes, Cecilia. That's right. Whether the sun's a liquid or a gas. Okay, and who cares? Why does it matter? 3 reasons. Back to the room. Yeah. So that things make sense. That's my favorite one. Yeah. It might be okay if a poem doesn't make sense, but science is supposed to be this very objective description of an understanding of how something works. That means that I tell you how I think something understands and you understand exactly what I mean, right? That's a very particular way of relating information to people. And there's no room for science to not make sense. It doesn't have an identity if it doesn't make sense. And I'm going to circle back on that because at the end of class last time, we were talking, at least up here in the front, we were talking a bit about this kind of reversion to supernaturalism that's happening in the world, at least in the West, and perhaps in our country right now. So I want to get your guys' thoughts on that before we cruise on. But first, what are the other 2 reasons? Who else? Who else has an idea? What are the other 2 reasons why it would matter if the stars are liquid or a gas?
So see if we can do fusion here.
Yeah, so fusion, right? It's kind of this holy grail of energy production, right? Ideally, we just squish some hydrogens together and we get energy back. We get power out of these things, right? And there's plenty of hydrogen on Earth. Where's most of the hydrogen on Earth? Yeah, Zach?
In the atmosphere.
There's a lot, but where else? Yeah, even more. In the water, yeah, in the oceans, right? The oceans are basically mostly hydrogen, at least by count of atoms. Remember, water is just 2 hydrogens and an oxygen. Okay, so there's a lot of fuel lying around, and it can be processed cleanly. That would be a wonderful source of power. We don't know how we would do it. Certainly, the approach using these really hot gases has been an utter disaster. So if we don't understand how stars do fusion, we probably have no chance of pulling it off on Earth, right? Which is not to say that it's going to work out anytime soon just because we change our mind about stars, but maybe we have a chance. Still need a ton of pressure, and that's an issue. All right, and then the third reason, which is perhaps the least important, but it's fun too. What's the third reason? Who cares? Stars are liquids or gases?
I'm waiting.
What's that?
I'm waiting.
I mean, you guys have to nail these by the end of the class. So I'm never going to end the last class if you guys can't do this. I'll just somehow track you down in your dorm rooms and make you answer it later. Yeah.
Because everything downstream of it, every single black holes, the Big Bang, the universe, everything.
Everything, yeah, the whole story.
Even how our planet came to be, everything came downstream.
Exactly.
The sun is.
So all of these stories we tell about the natural history of the world we live in. So everything, literally everything, from how old our planet is, which constrains the kind of stories we can tell about how geological formations happen, to the ultimate fate of our solar system, to the story about the whole universe, where it came from, what are we doing here? These huge questions, which seem kind of detached, they actually constrain the stories we can tell about our own planet. And so, you might say that doesn't, who cares if we don't understand how the Earth was formed or something, and fair enough, it might not matter to you. I think it's interesting, but again, that's probably the least important piece of this puzzle. So as we move into these 2 stories, yeah.
I'm curious on the why does it matter front.
Mm-hmm.
If we've been using the gaseous model for so long,
Hmm.
and the liquid model is now like when was the liquid model first like uh, not discovered, but like hypothesized, and like how long has research been happening on this?
Yeah, so I'm not sure if you were here for this lecture, but we did some examination of the history in the 1800s, and there was a so I think the right way to think about it is that for most of rational science, this thing we call science, whatever its infant version was after the Enlightenment,
Natural
um,
philosophy.
yeah. So most of the history of the study of the stars, people did treat the stars as liquids.
Oh,
It's only very recently, in about knee deep into the 20th century, through a number of experiments that were collated together, that the stars were considered gaseous, and that was in order to supply a means to power the stars, right? So they didn't really have fusion at the time, and as soon as fusion became a possibility, the compressive nature of gases was very nice for supplying the temperatures necessary to pull off this fusion, similar to the ways they were doing it in laboratories, right? So we've been able to actually do fusion in laboratories with these giant magnets and gases and all that stuff for quite a while. It's just extraordinarily inefficient. It requires way more energy to pull it off than you get back out of the fusion reaction. So the other second part of your question, I think, is that it's been kind of resurrected in recent years, largely through the work of this one scientist who was actually one of the innovators of the MRI machine. This gentleman named Dr. Robitaille. And so the paper that you're probably going to want to reference when you compare whatever little piece of this picture you decide to do your project on, that paper is called 40 Proofs. It's sort of a line-by-line analysis of the standard model of stars. It's listed in the syllabus somewhere in Moodle. Maybe not in the syllabus, it's in Moodle. One of the first few weeks, I believe it's posted there. And so, yeah, so Pierre, who I've gotten to know actually, we just got off the phone with him right before I walked in here. He's championed this for about the last 20 years, and it's finally started to percolate up in various pieces, reaching, I think, the people that it needs to reach very slowly but surely. Yeah.
yeah, he has a YouTube channel, right?
Oh, yeah.
That some of the videos on the watch list.
That's true. Yeah, good point. So if for your final project too, I should have maybe I can go back and add this if I remember to the Moodle. There, Pierre has a YouTube channel. It's fantastic. It's a little high level. He's not very good at explaining the basics to people, but he has a YouTube channel called Sky Scholar that's very extensive and addresses lots of stuff. Most of the stuff we talked about in this class. Yeah.
Pretty sure one of the video assignments had us go
Yep.
write make a summary or review on
That's right.
this video.
Yeah. So that could be a good resource for you also when you whatever phenomenon you're looking to compare. So some standard model feature of the universe. I don't know. Maybe you pick black holes or white dwarfs or something. You can probably find a counterposition from Pierre, and then he's going to have papers published on Vixera probably, which I linked to you. So I really want you to pull in two primary pieces, at least two papers to compare. I want you to wrestle with these two explanations that are given and hopefully synthesize some new understanding out of it. Remember, one of the only reasons to go to college is to learn how to think. So you gotta compare different people's arguments and come up with what makes sense to you. Which I've tried to do as much as possible in this class. I've obviously given you the standard explanation mainly through the textbook stuff and the workshops, and we've been using the lecture to look at alternatives to that side by side. So yeah, hopefully you guys can come away with your own perspective on that as it unfolds. All right, yeah.
Like a style or
It's a presentation.
that's a presentation.
Mm-hmm.
Yeah, it's 10-minute video, right?
Yeah, you could work with somebody, make a little bit longer. But yeah, 10, 15 minutes. I think if you collaborate with anybody, you could do longer. It's all written up there in Moodle. But yeah, you can use PowerPoint slides, record it, open up a Zoom meeting and just walk through a presentation like that. That's probably the easiest way. The one thing you cannot forget to do is upload it to your Google Drive and share the Google Drive folder with me. I will not be able to give you a grade if you don't. It has been a disaster for at least one person over the course of this this time I've been doing this.
Give him.
I can't give you a grade. You're gonna fail the class if I can't get into your presentation. Well, I'll do everything I can to stop that from happening. But all right, sounds good. All right, so let's talk a little bit about where we left off. So, like I said, I want to get into what happens to stars as they cease to become stars. Let's say that, because there's really two paths. Now, the standard model, the standard gaseous stars, generally die really violent deaths. I would say, let's say, almost always, right? There's some exceptions to that, but they take so long to happen that according to the standard model, they haven't happened yet. So all the stars that have ever existed have either died or are on their way to dying. The liquid model, of course, is a little bit less exciting. There are occasionally violent deaths of stars, but it's not the norm. Liquid stars just kind of cool off. And so those are to kind of preview the two stories. Before we get there, let's review the birth of stars from last week, I guess it was, yeah. What does anybody remember that we talked about last week regarding the initiation of star formation, and kind of bring us up to the point where we have a star to talk about it all? Anybody? Yeah, right.
I forget exactly what they're called, but like the H molecule clouds.
Hydrogens, yeah. Yep, molecular clouds, that's a good starting place. So that's kind of where our nurseries are for little baby stars, right? Now, what's somebody remember what happens inside of these H clouds? What's going on in there? Yeah, Zach.
It's high something and low pressure. It's not high heat because it's low heat makes low pressure.
Yeah, but I mean, we need little dense places, right?
Yeah. So it's high density and low pressure forces.
So we need actually density to squish these things. Or sorry, we need density, and we use, there's pressures, different mechanisms of pressure. So I guess this is a good place to reiterate this. Under the standard model, almost everything that we talk about comes down to pressure driven by gravity, right? And I made an argument to you guys last week that pressure really has no business in gravity, mainly because of why. What's the deal with pressure? Yeah, go ahead, Dante.
Because pressure only exists inside of a container.
That's the main problem, actually. The main problem is that the standard model, they want to very conveniently talk about the sun having a surface. They want to treat it as if it is being contained somehow, but it has no real container. And so especially when we start looking about the initiation of stars, we're talking about them being somehow contained. This is very perplexing because all of these nebulas are not actually gravitationally bound to one another. They are doing what a balloon popped in space would do in everyone's intuition, which is dissipates. And yet, there are overdense regions. And so the standard idea is, this from the gaseous perspective, the way they get around this, they say that, you know, the newborn stars, perhaps dying stars explosively, send shock waves which overcompress the regions, and then gravity keeps doing everything like it always does in the standard model. Now, we're going to see gravity continue to make the front page with the standard model today. In alternative, what is an alternative mechanism for our liquid stars? And honestly, this is kind of creeping into the mainstream models too, which I kind of pointed out. Yeah.
Stuff keeps clumping together in the clouds until eventually it gets large enough to become a star.
Yeah, yeah. What's that process called? Cold winter day.
Condensation.
Condensation, yeah. So electrostatic interactions, right?
Yeah, so little molecules and little atoms becoming droplets being condensed into little droplets, and then big droplets condense into bigger droplets and bigger droplets, and so you have a really big droplet.
Yeah. So the cool thing about droplets is, you know, maybe once you have droplets, like gravity starts to make a little more sense, because droplets actually exhibit inelastic collisions with each other, right? So gases, they just knock off each other like billiard balls. Droplets actually have some deformation to them, right? They're actually treated as if they lose energy into light and heat and electricity, maybe even further chemical reactions as they collide. So you actually have a means by which things can slow down and start to aggregate in one place. And once you get a bunch of things really nearby each other, maybe they can actually start pulling on one another. Let's go Kevin first.
There's another thing we talked about was that it's not all gas. There are some like little particles of dust and ice in there.
Yeah. So I actually think that the last couple of weeks lectures about the birth of stars and what the ingredients that go into them kind of point at the drift. I think about it as like a paradigm drift a little bit, where it seems like the standard model is kind of queued up to really lean into this condensation process already, right? Because there's whole new journals of astrochemistry which are discussing the sort of chemical reactions one might expect at these initiation phases. Yeah, so and then of course we talked about how these dust particles are really complex. They have organic molecules, there's ice particles, there's little sheltered caves made out of carbon and at the micro scale. So there is stuff, there's condensed matter there already, right, that we know about. So the question is that an important piece of the puzzle? Or is it just gas clumping together through gravity, which is a little bit more perplexing. Yes.
I was going to say, if you've ever put like two droplets of water on like a sheet of like hydrophobic paper, and then you slide like you have them, just come toward each other. They just come.
Yeah, they love each other. Yeah. Water. Water is a really special liquid, but actually the hydronium ions that are proposed to be the condensation, the little droplets that lead to the condensed matter stars, they would also be highly charged and interacting similarly, right? So, yeah, it's condensed matter likes to clump together. Gases hate each other; they bounce right off. Especially the ideal gas laws too. So I don't know. We could revise the equations of state for the stars and say, well, they're not really ideal gases. There's something else. Then it's like, well, what is that?
But they have to be ideal gases for all of it to work.
Yeah, exactly. So the story that we're going to get into here in a second about these, we're going to slowly make our way to these bizarre, hyper-dense objects. I'm talking about the entire sun crammed into a penny or something, right? Those are only possible using ideal gas laws. And so you can't have it both ways, right? And the ideal gas laws kind of let you down on the formation side of things and other places too. But you certainly can't overcompress. You can't make these hyper-dense objects with liquids. It just doesn't really work out. So, yeah. So ideal gas laws, they are ideal, but the whole standard story of stellar collapse that we're going to work our way towards this week depends on them. So it's an idealization, but it's also the bedrock of the entire story that flows downstream from where we're standing in this whole story right now, which is talking about what happens to stars after they live their life, or after they stop looking the way they do. All right. What else? Did we miss any pieces of this? Of course, the actual ignition event is nobody knows. It's very hard to see. These are in dense, dusty regions. We can only theorize about it. So, yeah, that moment is a little obscure. What we can say is that, before the thing turns into a star, it probably looks like a really big droplet. And we have some of those big droplets lying around in our solar system, it turns out, right? Namely Jupiter and Saturn, right? They're basically big droplets of sun stuff that don't have enough stuff in one place to actually supply that pressure to do fusion in either one of our models. Not the kind of fusion that we would expect from our sun, right? This neutral hydrogen fusion. Now, stars do fuse other stuff. We're going to talk about that today. And of course, there's two very different models of how they do that, depending on whether you're on the liquid or gas track of this drama. All right, did we miss anything? Any questions from last time? Thoughts about star formation, building blocks? Let's talk about the fate of the stars then, I suppose. Let's get into it. Oh, one other thing. Kevin asked last time, where do neutron stars fit onto the
HR diagram.
good old HR diagram? And I said, I don't know. That's actually a good question, but I suspected they're down here somewhere with our white dwarfs, right? It is true, they don't fit onto the HR diagram very cleanly, but they would be, these things should be very, very hot since they're super luminous. They're also really small in terms of, they're very hot in terms of the spectral class. They're very small in terms of luminosity, right? They don't give off a lot of light. So they would technically be found down here somewhere. They usually don't make the cut though, because they're, well, they give off emissions in like the gamma rays and X-ray spectrums often, right? Which doesn't even fit onto our spectral classification system. It would be kind of off this map a bit.
What is a neutron star?
We'll get there, don't worry. That's going to happen by the end of the week. So neutron stars, we have to start thinking about kind of three types of, so in the gaseous model, stars, we will see today, they basically end up, their fate is that they're, kind of spent carcasses that can no longer do fusion, can no longer support themselves through the pressure of the radiation. So they collapse upon themselves. And, being based on these infinite compressibilities, they turn into either white dwarfs, neutron stars, or black holes, which are all kind of the same thing, but on a different continuum with all projected extremes. They're also mapped onto very real phenomena. So when we look out at the sky, we really do see very dim but hot stars, white dwarfs. We really do see sources of neutron, we really do see sources of X-ray and gamma emission that perhaps have gravitational interactions. And we really do see points in space that seem to have gravitational interactions, but no luminosity at all. That would be the black hole. So we do, these ideas are mapped onto real observational stuff. The question is, what is that? What is happening there? Is it a collapsed star, or is it something else? And so, of course, we have two different stories to tell. All right, so we're getting very close to being able to at least tell a couple of stories about this HR chart, this stellar classification system. And I think that we will make it through this week, hopefully, if everything goes right. I do want to save enough time to go through some of this black hole stuff, particularly because there's been these really famous imaging studies in the last few years of these alleged black holes. So I want to make sure that we have time to look at what the heck that is. If it's not actually a collapsed star, what's going on and how did we get those images? Okay, so yes.
I feel a little embarrassed to ask this, but I was often getting X-rays and gamma rays confused with one another.
Yeah. That's a good point. They're very similar. They're really high frequency light, but X-rays are a little bit less intense. They're a little bit slower than gamma rays. Gamma rays is just kind of this blanket term for radiation that's so high frequency that we just can't observe anything beyond that. There might be even higher frequency radiation than gamma rays, but it's kind of just this word that gets blanketed onto this ultra, you could think of it as super blue, burn your eyes out blue light, basically. It's really, really far on the blue spectrum. That's why I said, if we were going to put neutron stars on here, they wouldn't even fit because they're so blue, they wouldn't even make the chart, basically, right?
That's why Hulk should have been blue, not green.
Hulk? Yeah, it's the most energetic, it's true. Okay, so we got this, so we're building this out. I think, the standard model is a little bit more complex, and I want to make sure that we do it justice because Yeah, because I obviously have been expressing a lot of discontent with it, and I want to make sure that we go through the standard story, because honestly, the liquid story of what happens to stars is far less complicated, and I can probably tell you about it in 5 minutes at the end of class. So let's look at the standard model a little bit and see what the astrophysicists have concocted to explain these different stars on this diagram over the last 100 years. So, you know, we have to really start to think back at this point to our standard model of fusion. So in the standard model of fusion, where is all of that fusion? Where's the hottest part of the gaseous star? Does anybody remember? Yeah,
Center.
the center and the core, right? So, and for most stars like our own, they are only fusing simple atoms, the simplest ones, hydrogen, right? So they fuse them, and by the way, when they fuse the hydrogens together, what's the product of that? What happens when you squish two hydrogens together? Helium, yeah. That's kind of an oversimplification. There's a bunch of stuff, but helium is the atom, the new element, right? It's the birth of a new element, the second one on the periodic table. And so the helium just kind of piles up there inside of standard stars. And that's kind of where things start to pick up in terms of what happens when the stars exhaust that hydrogen fuel. So let's see. Right, so we basically said before, by the way, this is just worth remembering, that the lifetimes of stars in terms of how long they live for, I'm using the word live really poetically here. I can't think of a better word though under the gaseous model, because the stars are kind of these objects that come and go. And so I'm going to just sort of poetically refer to it as the lives and deaths of stars. I don't have any argument that the stars are alive. Maybe they are. I have no idea, but we can't say that. So the basic idea is the bigger the star is, the more pressure there is, the faster it's going to burn through its fuel, right? So that's really important to remember for the standard gaseous model, because under the standard gaseous model, once you run out of fuel, things start to get really bad, right? Because remember, the standard gaseous star doesn't have a container to hold it all together. The only thing that's allegedly containing all of this gas is the gravity of the gas itself, right? So, and the only thing that's resisting the gravitational compression is what?
Sure.
Pressure from what's pushing out? What's holding it up?
The gas?
In some part, yeah. But
Fusion in the core.
so the fusion gives off really intense radiation, gamma rays actually, in the core. And those photons bounce around. Remember, light literally has momentum. You can push a sailboat in space basically with light, right? So that light has a lot of push to it. And so in the standard model, the reason the sun is a sphere that's in this nice equilibrium is because all that radiation pressure is holding back the gravity that would just collapse it into oblivion otherwise, right? So that's the standard model. Of course, in the liquid model, the thing is made out of condensed matter, and so there's all sorts of tension inside of this material to supply the pressure necessary for fusion, which can happen throughout the sun. It doesn't need to happen only in the core. But the core is the only place where there's enough pressure in the gaseous star to supply the temperatures necessary for these fusion reactions. And so what happens is when the stars, the big stars, they got so much pressure, they burn all that hydrogen in their core really fast. And so the story we're going to tell about their inevitable deaths is basically equivalent to how big those stars are, right? They live very, I mean, goodness gracious, 1 million years is like a blink of an eye on geological timescales, right? I mean, there's arguments that humans have been around, like anatomically modern humans have been around for 1 million years now, right? And this keeps getting pushed back, but I think that there's been some recent reports of that. So this is an incredibly short amount of time for that's being proposed for the deaths of some of these stars, especially the really large ones, right? So we need to ask ourselves, why do they die? in this gaseous model. Now, in the liquid model, what happens to the stars as they age? I'll just kind of like tell this in parallel alongside this main story. It's really boring, though, I'll tell you that much. What happens to a drop of liquid as it cools off?
And as it cools off, or as it
As it ages.
it evaporates.
Yeah, that's a good point. It evaporates and it cools off. So that's pretty boring. So, of course, if we go back to our diagram, we're telling this really meandering, wandering story for the aging of stars under the gaseous model. We're about to launch into that, how the stars kind of drift off the main sequence. They go through this giant phase. They go through this dwarf phase. Maybe they explode violently at different places along this story. In the liquid model, most of the stars just go straight down the main sequence. They literally just cool off and drift down the main sequence, which is why we see almost all of the stars on the main sequence, right? That's the logic. So the stars just cool off. And by the way, what happens when a star cools off past the M-class stars, once it's super red? Yeah, Kevin.
I'd say theoretically it becomes a brown dwarf then planet.
Yeah, it just starts to look like a droplet again. Yeah.
Yeah, it goes from red into the infrared.
Red into infrared, yeah, and then eventually the thing is just gonna get cold. Super, super cold.
Dead.
Cold. I mean, I don't know. I'm not sure. That's why this word, I hate this life and death stuff, because it's an interesting discussion, but it's not really what we want to be talking about here. But yeah, they're metamorphosizing and they're evolving, right? And so, if you were, I think, how many people were here from last semester? There's only a couple of you. But we talked about how it's really interesting. You can actually set the planets on an evolutionary continuum as well, right? So the cores of planets look a lot like Earth's, actually. Some of these Neptunes and so forth. And there's actually a great deal of evidence to support the idea that Neptunes can transition into something that looks like an Earth, right? And if a Neptune, or let's say if a Saturn or Jupiter can transition by cooling off and undergoing dissipative chemical reactions and can turn into something that looks like a Neptune, then all of a sudden you can put all the planets on the same and stars all on one continuum, right? You could actually tell a story where stars actually cool off and eventually you end up finding yourself sitting on top of one in a lecture hall here at SOU. Yeah.
By transitioning into looking like an Earth, do you mean cooling off to a point where it becomes condensed and rocky?
Yeah, so all of we sort of already understand that the giant planets in our solar system have rocky cores already.
And are mostly liquid.
Which happen to be about the same size as us.
Earth.
And so we're also discovering processes that could lead to giant Neptune-like worlds losing their atmospheres, going through radiative processes that cook their atmospheres and lead to the accelerated chemistry that actually transform them into looking something like our planet. So that's kind of interesting. Maybe it's a little more boring than the story I'm about to tell you from the gaseous model. It's also kind of cool, though, too, because you have kind of one very long, slow process that results in most of the bodies that we observe in the sky, including the one you're standing on, potentially. So that's interesting. Yeah.
But this evolutionary story, the main problem with it in the current idea of science, right, is that it takes way too long.
Yes, way too long.
Millions of years.
Trillions of years, so thousands of billions perhaps, right? And that's just back of the envelope calculations, right? I mean, again, maybe trillions, thousands of trillions of years even won't be out of the question 50 years from now, but it is completely out of the question as long as the Big Bang is the constraining story of our times, right? Which is, again, like I ask you guys every time, like, why does this matter? Who cares, right? Well, maybe it doesn't matter whether people understand whether the Earth, where the Earth came from. Maybe it doesn't matter, but you're certainly not going to be able to tell the same story with having this Big Bang story versus one with let's say a different type of cosmological story. So that's kind of interesting. All right, so let's talk about what happens to these gaseous stars, right? They've used up all of their fuel. Again, when the liquid stars use up their fuel, they just get cold, all right? When the gaseous stars use up their hydrogen in their core, what happens? Yeah.
Will they either explode or shrink?
Yeah, both actually. So let's talk about that. So what happens is that they kind of go through a process which is cyclic in that sense. They kind of go through processes, sort of shared processes of giving off material and shrinking simultaneously. The core, of course, is starting to crush down on itself because there's no longer that radiation pressure. Now, the standard story goes that as that core starts to collapse on itself without the radiation pressure, two things happen. One, the outer layers, the gas in the outer layers of it, it's not really, let's say, it starts dissipating in some sense, right? Which is, we'll come back to that. The other thing that's important is that all of that compression in the core leads to new pressure situations that can perhaps, well, let's just say allegedly drive the helium that's left over, all those leftovers, right, our spent fuel from our sun, the helium now gets compressed. So once the helium gets compressed, then it can ignite into fusion, where the heliums start to combine. What happens when you start smashing heliums together? Any ideas? Yeah.
Oxygen?
Yeah, oxygen, carbon and oxygen. Actually, carbon first, and then carbon will tack on another helium, and you'll get oxygen. So yeah, you start to be able to make bigger elements under this model, which is tantalizing because we do need to explain where big elements come from. That's a big task for everybody. And the standard model supplies this in stars. We'll have to get into it with liquids in a little bit. So that's kind of interesting. So what happens? What do you think happens when this ignition moment happens?
When it starts fusing helium, you mean?
Mm-hmm.
Does it blow up?
Yeah, it leads to some destabilization, which actually sends like these thermal shocks throughout the system, right? This actually drives the outer layers kind of outward in some sense. Actually leads to them casting material off. Now, again, this isn't a story that I personally subscribe to, but this is the standard story. I want to be like absolutely clear about it. So what happens in this model is that the fusion of that helium actually drives quite a bit of heat into the gaseous star. Now, there is actually a little bit of hydrogen left over in the standard model of the gaseous star. Why would that be? Why would there be some hydrogen that hadn't been fused? Yeah.
It's in the outer layers.
Yeah, it's not in the core, right? So remember, it was only hot enough in the core of the gaseous star to do that fusion. So when you get this extra boom of helium, it starts cooking off the hydrogen as well, right? And so as this hydrogen heats up, it's also expanding, right? This is sort of, this process is probably very familiar to anybody who's heated up a pot of water or something like that. And the result is that the stars kind of swell up to these enormous scales, right? Now, as they swell up, they're actually cool. The surface is actually cooling. This is so when gases expand, they cool, right? So this is kind of the principle. You guys probably use air conditioners in the summer, right? It's kind of the same thing, right? You just cycle gas where you compress and allow it to expand. It actually cools off the materials that are containing it. And that's quite productive. You blow air across it and you're happy again. Same thing's kind of happening at the surface of these. That's why the surface appears red, right? Because red is cold in astronomy, right? In physics, red is cold, blue is hot. So these expanded stars, they're kind of doing this adiabatic cooling process at the surface, and they have this appearance. So they're fat and cold. Okay, some of them are enormous, by the way. That's the sun. This is Delta Bootis, and then this Cygni? I never said that out loud. Enormous. It can't even fit it onto the screen compared to it, right? Now, I told you guys earlier that you couldn't really measure the angular resolution of stars with a telescope, which is true. I was looking into it because I was trying to make up my mind about whether I thought that these red giant stars were actually giant or not. And it turns out that they actually have measured these using these interferometry techniques, which I don't really want to get into a tangent on right now. But we do have some angular resolution of some of these. So I think it's pretty safe to say that they are actually really big stars. Now, there aren't that many of them though, right? So if we tell this story, if we go back, I'm going to just zip back to our HR diagram. We have a pocket. This is overrepresented in all honesty, but there's a pocket of these giant red stars off to the upper right here. So the standard story is that those stars are transitioning, they're peeling off the main sequence, right? As they undergo this helium flash, they undergo this kind of expansion of their surface. They're really losing material at the surface at this point. So what happens? Well, of course, where they peel off from the main sequence is going to have to do with how much stuff there is. But let's get into the construction. So what happens is that this core keeps compressing on itself, right? And there continues to be ignitions of new layers of fresh hydrogen outside of the thing as we move along, right? And this again further accelerates the expansion of these things. But it's a kind of oscillatory process in the standard model, right? So you actually have stars that start to peel off the main sequence, they expand, they're doing this thing, but then, they use up one layer of their helium or their hydrogen, and they get smaller again and kind of drift back towards the main sequence. And then maybe they do it again, and they could go through multiple layers of this business, right?
I feel like I'm looking at the Ptolemaic orbitals again.
Yeah, it's pretty wild. So again, no one's ever seen any of this happen, right? This is even for these really huge stars in the standard story, they last for 1 million years, right? And so even with the fastest version of this would take thousands of years for them to do a single motion off of this main sequence. So we haven't had time to observe those. Maybe 1,000 years from now, that question can be answered definitively. But the standard story goes that these things kind of oscillate around in the giant phase for quite a while. Now, at some point, they're going to exhaust all that central helium, and they're not going to have anything left to burn. And that's a really big problem for a gaseous star, actually, because like we kind of previewed at the beginning of this, once there's nothing to hold on to, once there's no fusion to push back against gravity, and the outer layers are cold and they've been kind of shoved off, you actually get something that looks like this. So these are some of the most, maybe some of the most dramatic and perhaps beautiful pictures that we really can get from telescopes. You can actually see some of these things with a regular old telescope too. I think these are quite false colored, but you can still see some of this stuff in the visible. These are called planetary nebula, which have nothing to do with planets, unless perhaps, unless planets are stars, but old stars. But they have nothing to do with planets. Why do they call them planetary nebula? Kevin?
Because at one point we thought that this was how the planets formed.
Yeah, people thought they were solar systems when they looked up. They weren't, most people were making their own telescopes in the early days when this stuff was going on, so it wasn't so clear what was what. And it's actually a reasonable guess. One thing you'll notice about these planetary nebulae, which is quite fascinating, is there's always a little star in the center, right?
This is a dumb question, but
There's no dumb questions. It's okay.
different colors due to the different type of chemicals.
Yeah, that's right. Yeah. So, and actually, I could teach a whole class on planetary nebulae because they're fascinating. So from those different chemical reactions, so the light reflects chemical reactions. Now, the chemical reactions that we find in planetary nebula are not the chemical reactions of gases with one another. There are tons of reactions that are apparent in these nebulae that are only possible with little droplets of stuff. They could only be catalyzed by condensed matter. So that's a whole other story and quite an argument against the gaseous stars. Yeah.
If I remember right from the textbook, it mentions that when stars go supernova, the star can actually be shot out of the nebula and not be in the center, or even just be off center.
So these are thought to not even be from supernova, right? So these would be
It would be like what our star does, right?
yeah, something more like our star, kind of middle of the road or smaller star. The supernovas are supposed to be so violent and extreme that they sort of dissipate very, very quickly. I'm not sure that this might be called, these might be considered nova of some sort. That might be possible. I'd have to go and look at that, how that word is used, which are just sort of smaller explosions. But yeah, there's clearly evidence of some sort of explosion that's happened here, right? I mean, something has been blown off. It looks like in many of the cases, this is kind of going too fast, I'm sorry about that. It's a GIF. I had no control over it. But you can see in some of them, there's actually multiple layers of structure. It seems like multiple events have happened, like boom, 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 or whatever. And some of these processes, based on the extent of their expansion, could have taken, a very long time, certainly thousands of years for these structures to appear. So yeah, something violent has happened here for sure. But what's really interesting about these things is that there's a little star left in the middle of them, right? And it's not a particularly cold star, right? So these planetary nebula almost always have one of these things that we've alluded to, these white dwarfs at the center of them, right? Okay, so we've kind of reached that point, I think, where we have to get into white dwarfs. Before we do that, let's talk about what might be happening here. Because, if the stars are liquids, as I've kind of been advocating for, then we still have to explain this, right? We still have to explain red giant stars. If they are actual giant stars, and it seems like they are, what the heck is happening, right? Any ideas?
I was going to ask how does this work?
Yeah, it's a good question. It would be insane if we didn't figure this out before we moved on. Well, there's some first principles we might be able to apply to answer that question. So, what kind of things do we have available to us in the liquid stars that we don't have available to us in gaseous stars? What's kind of the main thing that separates the way that we would interpret almost anything about the stars? Yeah.
Fusion can be happening anywhere on star.
That's a really good point. I hadn't even thought of that, but that's absolutely right. And why is that?
Because of how liquids work as opposed to how gases work and like pressure.
Because the liquids can confine stuff in between them, right? So especially these very specific kinds of liquids. Now, water is one of them. Water actually forms layered-like structures as well. Water also forms hexagonal lattices, which is really important in terms of generating a black body signature or a Planckian signature like we see on the surface of stars. So we suspect that there is some sort of that hexagonal arrangement of the hydrogens, which makes a nice layered system, right? Remember, those black bodies that we use to make the sun's spectrum in laboratories, they're made out of layered hexagonal materials, right? So, and water does that too. So, water can trap things in between its layers. Goodness gracious, I mean, I assume if you had enough pressure, maybe you could fuse things. You'd probably do something insane to your water first. But the idea is, yes, you can trap stuff in between those layers. You could trap hydrogens. Maybe you could trap other stuff. Yeah. But I think you're on the right track. So yeah. It's structural, right?
Basically, my thought was just the condensed matter. That's like the main thing that a condensed matter star has over a gaseous one.
And what does that afford it? I guess I'm kind of dancing around the point here.
Well, aside from what you guys just talked about with the fusion, um, it provides a container, a structure,
Structure, that's it. That's the word I'm kind of looking for.
yeah, like a lattice that
Structure, right? So we have the ability all of a sudden for there to be different structured regions, actually. And that might be a problem for some stars, actually. So if you think way back, I don't expect you to remember this, but we talked a little bit about the solar cycles, right? We talked about how there's this weird thing, we get sunspots every once in a while, and I think that I laid down for you the hypothesis that perhaps in the liquid model, sunspots are actually this process by which the star kind of burps out impurities, including gaseous impurities that might be sublimating in its interior. And that as the core is doing some sort of cyclic process, maybe it's tumbling, which would explain the reversal of the polarity and so forth, that's very predictable every 10 years. Maybe these impurities are getting expelled by the solar activity. So we get sunspots, they're basically little burps, and that's really healthy for a normal star. It's really healthy for it to burp out its stuff. What happens if a star can't burp out these impurities? What happens if it can't burp out its bubbles? What happens if you can't? Anybody ever had really bad gas before? It sucks, right? It's horribly painful. Don't act like you haven't. I know you all have. Yeah.
well, the pressure of that gas increases as there's more of it and more of it. If it can't leave, because gas wants to leave, and impurities they want to go. If it can't, that pressure is just going to keep building so that it will either find a way out or force its way out.
Yeah. Yeah.
Like if you pump a tire too much, and then either there's a hole and it will come out there, or it explodes.
Or blow the tire, yeah. So when we think about these catastrophic situations like these planetary nebula, when we see evidence of an explosion of a star of some sort. Now, not totally catastrophic, because again, there's still a star just chilling at the middle of these planetary nebulas. So they're not totally gone yet, right? But something bad happened. It lost its outer layers. The way that we can kind of bring this in line with the liquid model is that our liquid star is an onion layered structure. It has layers of this hydrogen liquid lattice, right, all the way through. Perhaps the core is in a different configuration. But hydrogen can, just like in the core perhaps, hydrogen can actually bond in different ways, right? Just like carbon can, right? You can bond carbon into a cubic crystal, you get a diamond. You bond it into a layered hexagonal lattice, you get black soot or graphite, right? Very, very different situations, and it's just the bonding arrangement. So we have a situation where it's possible that in some minority of stars that are just plain unlucky for some reason that we don't totally understand, that their interior structure hasn't been able to accommodate the outgassing or of these sublimating impurities, right? So you can imagine little bubbles forming, and as long as you can get them out, you can pass the gas, you're fine. But if you can't, if there's some sort of a blockage that could be structural, right? There could be literally solid obstacles to the passing of the degassing. You could get into a place where there become huge, let's say vast instead of huge, vast bubbles that form kind of these laminated pieces of the star, which would, ultimately cause perhaps different layers of that balloon to burst, right? You can kind of think of each one of these as a bunch of balloons inside of balloons at that point. So this is a pretty underdeveloped model, but it is maybe a hint of what could be happening. That's why I think in some sense that what we're seeing here with the liquid star revolution is less of a revolution and more of a renaissance, because there's so much work to be done if we change our minds as scientific people about how to go about explaining these things, right? Yeah.
This class made me like my ear perked up when you said for some now they have a different structure for some reason we don't quite understand. And I'm like, but But we must.
But we must. Yeah, that's cool. I mean, look,
But why?
what's that?
But why?
But why? Well, that's what we do as scientists. Yeah, we try to understand. Look, this is the equivalent. Like the model that I'm giving you here is the equivalent of, you know, people coming up with models for, it's kind of the equivalent of Copernicus saying that, hey, I think that instead of the Earth being at the center of the solar system, the Earth actually goes in a spherical orbit around the sun. And everybody was like, that's idiotic. It can't possibly be a circle. And he was like, well, yeah, but I don't know. It just makes more sense, right? Now, look, his detractors, Copernicus's detractors, really, Copernicus died by the time this was published, but let's say the Galileo's detractors, they had a good point. Those circular orbits didn't work, right? And so it took another generation for people to come along, namely Kepler and everybody who came after that, to kind of iron it out and be like, oh, you know what? Copernicus was still basically right. And the mathematicians were right that he was wrong, but he was right in principle because they're ellipses. Not only are they ellipses, they're barely ellipses for the most part. They're basically circles. They're just not mathematically perfect circles, right? And so, some model like this that I'm just throwing down right now, this is a very infantile, it's very nascent. It's a newborn idea. So there's tremendous amount of work, and I'm sure the subtleties of it could keep people busy for the next 500 years. And that's what's actually really exciting about it from just a dorky scientific perspective. There's a lot of work to be done all of a sudden, as opposed to kind of acting like we understand how everything works. Perhaps we have a lot more work to be done than we thought. Okay, does that make sense? So that's our liquid proposal for giant stars and for planetary nebula. Both of these have to explain that little bright white star. Sorry, that little dim white star at the center of the planetary nebula, because that's a really strange phenomenon. So let's take a look at that thing. Some more explosions. Oh yeah, we should probably talk about massive stars too. So the massive ones actually basically do the same thing that we talked about already with the kind of run-of-the-mill stars. The only difference is we have more opportunity for greater heat, means we can have greater fusion products, right? So we can fuse stuff. We get layers that are capable of fusing all the way up to iron, really, which, yeah, I wish I could pull this up, but...
Why does it say ash?
Where's iron on this thing? It's like about halfway down the first metal row, right? So it's pretty big, but it's not that big, right? Yeah.
Why does it say iron ash?
I guess because it's not fusing.
I can answer it.
Yeah.
It's because the textbook explains the fusion in a really weird way by saying the hydrogen goes into helium ash, or the helium goes to carbon.
It's like the leftovers.
Huh?
Like the leftovers.
It's pretty much just using ash as a filler word for leftovers, yeah.
It's like the product, right, of the fusion reaction.
It's not really ash, it's just what's left over.
Yeah.
Okay.
Like what's
from a fire? Okay.
Yeah. Now, what's really cool, I mean, it would make sense in either the liquid or the gaseous model that the bigger your star is, probably the bigger elements that it can fuse, right? Because you just have more pressure. In either case, I mean, this is a very, let's see, there's a lot of epicycles here. It's a very complex picture of how all of these fusion reactions happen in the gaseous star. In the liquid star, probably just the bigger the star is, the more fusion on balance it can do in terms of larger elements. And there are some pretty enormous stars out there too. What's kind of interesting though is, like, if you look at just the elements here, right, these are basically like what the Earth is made out of, right? Kind of from the outside in some sense, right? We've got a lot of these and kind of in a similar proportions, right? So the stars really have this they have a really beautiful congruence with the planets in some sense, which is quite tantalizing in terms of how all that happens. Because yeah, you can make complex chemicals like water and the nitrogen, molecular nitrogen in our atmosphere, or the soil. These things can all be made through chemical reactions, but the elements, the atoms themselves, They have to be made in super pressurized environments. We have to do this fusion somehow. You have to somehow smash these atoms together. So if you want to make a helium, you got to smash it together inside of a star, and that's the smallest, smallest atom you could make, basically, right? You want to make an iron, you need a lot of pressure, right? And so those are our building blocks. Those are what we use to do all of the chemistry that we see all around this room right now. All of those individual atoms that are reacting with each other, they had to have come from some super high pressure environment for the most part. So that's tantalizing. All right, so these big stars, we'll come back to the deaths of the big stars because this is our supernova story, and we'll give it its due diligence here on Thursday, I think. I do want to spend the back piece of this class talking about our good friend, the white dwarf, though. That star at the center of our planetary nebula, right? After the star presumably has cast off its outer layers, we end up with another star in its place. That star is very, very hot and very, very dim. So, of course, in the standard model, this is a natural piece of the aging process for a run-of-the-mill star like our sun, right? The story goes that stars that are kind of garden variety like ours, they will all go through this process where they use up their fuel, they go through these convulsions, lose the layers, and ultimately they find themselves here. Now, of course, this makes a lot of sense from the standard model, right? Because the standard model says that once this star, the core of the star, has cast off all of its outer layers, it can no longer do fusion at all. It has nothing left to burn for the amount of material that's there. It can't generate pressure. It's used up all of its external hydrogen. It can't do the helium in the core. It can't do anything. It's got nothing. And so without any source of fusion, there's nothing to fight back against the gravity in that story, right? Perhaps the ideal gas collisions would be a problem too, but I won't even pick on that. Let's just go with it. So the gravity takes over in these stories. Now, why do they think that? Why do they think that these little, well, I'm not going to call them little. Why do they think that these white dwarfs, these dim, hot stars left over after these explosions, why do they think that they're little? Yeah.
Because they're dim.
Because they're dim. Remember, for the gaseous model, they have no structure available to them. So the only way they can make something dim is by shrinking it, by changing the radius. I think I pulled that equation together here somewhere. Yeah. So the brightness is always proportional to the radius. They ignore the emissivity terms. And so the only way to make something like that that's hot and dim is to shrink it, which fits really nicely with the story that they already have going about these gravity kind of doing everything, right? Because, well, the things just collapse. It's a very self-consistent story, which you honestly got to applaud them for up to this point, because one of the best things we can hope for in a scientific theory is that it's internally consistent, and, well, they're more or less internally consistent here. Now, this is pretty crazy, because the idea is that as the radius decreases, even for so this is in terms of 1 on this axis would be the size of our star, 1 solar radius. Basically, at some point, without any of that radiation pressure to hold the thing up, it's going to collapse down to this really tiny radius, right? And then you can guess what happens when you get bigger than 1.5 times the size of our star, right? That's when we get into some of this really, really collapsed stuff. And that'll lead us into our discussion of black holes and neutron stars. Hopefully we'll start that next class. So for ours, though, it's collapsing down to kind of this really, really, really tiny radius. So again, the standard story, when these stars lose their ability to fuse, there's still a lot of stuff there, the ash, all the ash is left, right? and there's nothing to push that ash outward. No radiation pressure, no gas pressure. And so the thing just starts falling into itself, right? Now, there's a couple of problems with that. Even if we imagine, so there's a couple of problems I see with that, and one of them is going to become more clear when we start talking about relativity as it's applied to cosmology. So we have to take a little diversion next week about relativity. It's at the heart of the cosmological story of the expansion of the universe and all of this. But it really starts to shine light on the idea that standard physics doesn't actually have a material explanation for what gravity is, which is really, really interesting. So, from where I'm sitting, gravity is simply atoms pulling on each other, right? Because they're literally knitted together with their neighbors. That's pretty boring, but for the standard approach to physics, gravity is just a measured parameter. There's no real material cause for it. Certainly isn't understood as something atoms are doing to each other. And so it's just a variable that results from the amount of material that's in one place.
Yeah, and they're even, I keep hearing about, we're going to find the graviton, but guys, we're going to find the particle that does gravity, and like they never do.
What's a gravity?
Yeah,
It's
well,
the name for the particle that does gravity.
yeah.
Is there
Be a sooner particle?
No, it's a hypothetical name.
Well, everything's a particle, right?
It's just math.
Everything's gravity, everything's a particle.
Particle is just like a point that is a bunch of equations.
Yeah,
Basically.
that is absolutely true.
A point explanation for gravity, and that doesn't work because that's not how it works.
Yeah, there's no way you're gonna actually have physical particles like motes of dust that somehow hit each other and pull on each other. It doesn't actually make any sense. Yeah, go ahead.
in the textbook? It says like the theory of relativity is kind of, or I might be thinking of it wrong, but it kind of explains gravity, on the plane of mass and everything.
Yeah.
Like,
Is it?
it doesn't define it as a particle. It defines it as like this potential energy that as you get more mass, the more gravity you have.
Well, it's an explanation for why the more mass you have, the more it's the idea of like it bends space time, so then things fall toward it, right?
We're gonna deal with I want to do relativity. It's full justice. So we can't do it in 10 minutes. There are some serious what I'm pointing at here is that general relativity is an extraordinarily accurate way of relating in experimental systems. It does a great job of relating parameters like mass, right? Like temperature, like spatial components, right? So length, width, height. It does a really good job of relating those things to each other. It doesn't make any attempt to explain to you what they actually mean, though. So the relativists have no idea what mass means, actually. They just know that it's a measurable quantity, right? If you really want to understand what mass means, you have to go back and understand how it was first introduced into physics, right? And it was introduced through gravitational experiments originally. Now, at some point, we started using the word mass for electrical interactions, which was perhaps a massive mistake, actually. That was a joke. It was I'm trying to stay awake here, kids. So there's been a conversion of the original intent of mass, which was a gravitational inertial descriptor, to something that just means the equivalent amount of force necessary to deflect a beam of electrically charged gas, essentially, inside of these vacuum tubes. So, and then you can scale that out to your giant Large Hadron Colliders and everything like that. So the word mass is problematic. My point is that you can build a very eloquent, sophisticated equation that relates your observables using these parameters that you can measure. But what does it mean? What does this thing called mass mean? I mean, it's an idea, it's a quality that's measurable. It's not a thing that I can just toss to you, right? It's not a physical body. Although Newton really wanted that to be what it meant originally. Yeah.
I guess let me I know you want to give relativity its due diligence, but assuming like the general idea that like space-time and like bending space-time is real, the thing is the theory never explains how mass bends, like how mass bends space.
That's exactly what I'm getting at.
It
It's
just,
not.
it says it does it, but there's no explanation for how, because that wasn't the goal.
Yeah, it's not a material mechanistic science. It's really just a mathematical relationship map. Okay, so the problem is that once we start confusing our maps for the physical territory that they represent, we can push those equations well beyond what they're designed to do. And that turns out to be what happens downstream of this, including with our white dwarf, right? Because if we don't know what mass means, and we assume that if you have a bunch of atoms in one place, that the more of them you get in one place, that the more they pull on each other, that mass is going to do the gravitational business. And we're using ideal gas laws for these little particle thingies, which Dante pointed out. Particles, in all reality, are just instantiated measurements or predictions of what you would measure, right? So they're not even physical objects to begin with. And now we start applying gravity to these measurements, and we're just off in some completely insane fantasy land very quickly, actually. Now, that doesn't mean it's not sophisticated mathematically. It is. But math can lie to you all the time. It's actually really, really easy to fool yourself with mathematics, because mathematics is just quantitative logic. And if you don't have a physical understanding of what your parameters mean, then you can push them into fantasy land very, very quickly. And so that seems to be what's happened here with all of these collapsed objects that we're talking about. Like I said, this white dwarf, the idea is essentially that, since the star is made out of these particle thingies at this point, that it's going to, the mass of these particle thingies is going to essentially result in the gravitational collapse of these things. And we end up with our star, all of the material, that ash that's left over in our star, being crammed into something smaller than the Earth, right? So it's like if you took the sun and just put all of it, all the leftovers anyways, into a tiny little place. I think it actually would be quite a bit smaller. I think it's actually like the size of a quarter for our sun when it becomes one of these white dwarfs. It's really, really preposterously small. Okay, so that's one possibility. Now, of course, in the standard model, what would happen is that those giant stars are going to drift across the entire chart. They're going to find themselves now down in the super hot and super dim region, right, as they have gotten smaller. Of course, and this is the last piece of the puzzle that I want to feed you guys before we get into supermassive stars collapsing. With the liquid model, we have structure. So optical properties can be derived from structure. The diamond and the soot are both made out of carbon. The only difference is the bonding arrangement of the two. The diamond is an incredibly poor emitter. You will not get a nice spectrum. It will look very, very dim, right? The carbon is going to be very, very good emitter absorber. It's going to look very, very bright. All of its temperature will go into light and vice versa. So again, graphene, and you squish it, you get a diamond, right? Graphite, sorry. So we're actually talking about phase changes in the liquid that result in the different optical properties. This means that our white dwarf star for the liquid model isn't a smaller star. It's a regular sized star. It just has undergone some sort of wild transformations during that moment when it was losing its outer layers. It isn't a normal part in the life of a star. It happens to exceptional stars that have had really disturbed internal structure. They've had all of this right? They're sick patients. They couldn't pass that gas, right? Terrible things are happening in these stars. They're structurally anomalous. So the white dwarf, the red dwarf, they're anomalies for the liquid stars. Most of the liquid stars just kind of cool off, right? All of the stars that are gaseous, however, are subject to this incredibly violent fate. And the fate of the really large stars is quite fantastical. And so I want to give that one, the black holes, the neutron stars, we need to kind of really pick apart the ideas behind that and see if we can make sense. And this will lead us back to gravity. This will lead us back to the concept of mass, perhaps the misapplication of the concept of mass. Yeah, one last thought.
You said before with the graphite or soot like compresses into this new lattice. So wouldn't that, even if it's a slight compression, wouldn't that still mean that the white dwarf is slightly more dense?
It could be the core of a star.
Okay.
Yeah, because the core, we can observe differential rotation of our sun's core just from helioseismology studies. So it seems like it has a different structure than the exterior. It seems like it rotates differently. It's more solid in a
So
sense.
would the white dwarf in the liquid model still kind of be the core of the star
Yeah,
that just shut off its outer layers?
yeah, absolutely. Yeah,
But like the reason is that it's super dense is not that it's ultra dense, but just that it's a different structure. Okay.
exactly. Yeah, yeah, yeah. It could be pretty big still and heavy, and which would give us our orbital dynamics that we need to bring some of these systems and these multi-binary trinary systems into line, right?
Interesting.
Yeah. All right. So that was a little rushed. Let's review this again, and then we'll get into black holes, neutron stars, gravity, relativity, and ultimately cosmology before this whole thing is over.
That sounds.
All right, guys. Yeah.
Oh,
Have a good week.